parts that I found between other famous teachers' point about this object recognition in recent paper. Not much more recent, but we can say, okay, they are informative data and some new parts about it. I plan to have three example also in the MATLAB with this section. Mainly this part nowadays wrapped to the concept of deep learning that it's not our talk, but maybe I will give you some task regarding that. Some of you also do your presentation part with the aim of this object recognition, but now we will have some theoretical parts and some foundation informative parts about this topic. Let us see what we cover. We cover all these blocks. Just object recognition and representation and description will remain as I highlighted here, and our journey to DIP will be over by this chapter. As I tell you, somehow this chapter is, we can say it's optional and due to the teacher that they will teach, but because we have time, this is our maybe last week, let us talk about it and have some information, because nowadays, my friend, after these lectures, we have another topic which is more famous and more applicable. People call it deep learning. I don't know, maybe we have some course about it, or maybe we don't have. But what I know that if we want to have some informative lecture, we should finish with these object recognition parts also. Also, as you know, we have done this image compression and color image processing. You know, all these box is full, just this object recognition is remain. First of all, let us see what is object recognition, which is the computer vision technique for identifying the object in image or video. Somehow people know this object recognition as a key output for the deep learning and machine learning algorithm. And when human look at some photograph and watch a video, we can readily spot people, objects, sense, and visual details. And the goal is to teach the computer to do what comes naturally to human, to gain a level of understanding of what an image contains. Suppose if I have one cat and dog, and then I want to enter them inside of my object recognition algorithm, I should distinguish, or I should identify which one is dog and which one is cat. Exactly what I showed at the top. Object recognition is a key technology behind the driverless cars, also enables them to recognize the stop sign or to distinguish the pedestrian from the lamppost. And it's also used for a variety of some applications such as disease identification in bioimaging, industrial inspection, and robot vision. Let's continue and see what will be the difference between now this object recognition and object detection. Object detection and this object recognition are similar techniques to identify the object, but vary in the execution. We can say that object detection is some process to finding the instances of object in image, and in the case of deep learning, this object detection is the subject of object recognition, where the object is not only identified, but also located in an image. This allows for some multiple objects to be identified and located within the same image. Suppose in the figure, the recognition is at the left and detection are on the right. Okay. Then it may be a little bit different from the principle and application. What we will talk for you is we will talk regarding the object recognition, okay, for you. And object detection part uh, may wrap more to the deep learning application. There are some models for this object recognition topic, which we can say it's rely upon the existence of set of predefined objects. We have some object, we have some model based, and some recognition system, which based on that, you can give the output that suppose the image that I have here is circle, triangular, or rectangular. What is that? If I want to tell you some simple concept or simple word about this recognition part, it's something like that. I have picture of you and then searching in a city about you. I will match your feature or your picture elements to all, and then I'm going to see that are you really, is it similar to you or no? And then based on that, I can recognize the object in the image. But if I want to exactly detect you, I should now use the image of you. Okay, two things. One is that recognition is that just finding, suppose Kaya in the image, or any person or any human or anybody in the image. And then detection is that I recognize the Kaya, or I find the Kaya, or I detect the Kaya. Don't mix the word together. Some object recognitions or object categorization can be something like that. Suppose if we want to find the airplanes, we want to find the motorbike. As you see, there are a variety of them. Cars, cars rare, suppose background and all. These are the recognition. Okay? Suppose you just want to find a person, in any person. This is recognition. But detection is that you aim with Kaya in the image. Let's go on and see what will be the main step. In this topic, the main step will be some parts like preprocessing, which is the model database, is built by establishing the association between the features and model. Next will be the recognition, which is the sense feature are used to retrieve the appropriate association stored in the model database. And some challenge we have something like the appearance of an object can have the large range of the variation due to some viewpoint when we will be change. Shape change, for example, non-rigid object. Some challenge like photometric effects and sense clutter all will be the challenge that we have. And different view of the same object also can give the rise to widely different image. Suppose if we see one glass from different mm, looking side or view, it may become mixed or it can be confused our algorithm to detect it. It's exactly the glass or I don't know, any other object. Something that I want to add, somehow the distance between the camera or acquisition system, image acquisition system also will make some different concept regarding the image. An object which we have in that. What we have, or let us say what will be the requirement. The requirement will be some invariance, I mean the geometric transformation or translation, rotation, scale, caused by viewpoint change due to the camera and object motion. And some robustness is some noise that we can have, some detection error, something like edge or corner detection, illumination and shadows, Partial occlusion, for example, self and from other object. In intersync shape distortion, something like non-rigid object will be the robustness of this topic. Yes, next. Um, but what will be the performance criteria for this subject? We have four elements that we should consider. One is the scope, what kind of object can be recognized in what kind of sense. Robustness is that does the method tolerate the reasonable amount of the noise and occlusion in the sense, and does it degrade gracefully had those tolerance are existed. Efficiency is that how much time and memory are required to search the solution space. Accuracy is that correct the recognition, false positive or wrong recognition, or false negative is the missed recognition part. Um, and if we want to talk regarding the approaches, differs to according to suppose restricted on the form of the object, which it will be in 2D or 3D, simple with complex object, rigid with deforming object. Representation scheme, something like object is center or view is center. Matching scheme, something like geometry based, like shape and that. And appearance based, something like eigenface. Type of the feature, suppose, is it local that people will call it SIFT, or is it global that people will call it eigen coefficient? An image formation model, which is that it's perspective projection or orthographic projection plus scale, or affine transformation for planar object and that. There will be the approach which differ according to any these topic of this type of image processing concept. Uh, when we talk about the representation scheme, we are thinking about some concept, which suppose this is from this paper that I highlighted at the bottom, the model-based recognition in robot vision. We can have object which it will be center, or it can be viewer will be center. Means that viewpoint will be if you see the camera and from the top, and if you see the object or something at the uh, suppose this place with the 3D modeling, then viewer points to the object will be one circle about this height, and then this camera can be any place like that. And suppose when our object center representation will be suppose a 3D model of the object, we have some advantage like that every view of the object is available, and but might not be easily to build when we have the object at the center. But to different matching approach, we can have this object centered representation. Suppose in the 3D and 3D, which in that we reconstruct the object from sense and match it with the models. For example, when we are using the shaping of X method, we will talk later, or 3D to 2D, which is the back project candidate model onto the sense and match it with the object in the sense, which requires the some camera calibration. 3D to 2D, it's something like that. Now, if we know the object with the 3D dimension in the world, and you take the camera, you convert it from 3D to 2D, okay? Because you will put it in the image, and when it's come to the image, then it have X and Why? Okay, go on. Viewer center representation, which is the objects are described by the set of characteristics, views, or aspect. We can have some advantage, which is it's easier to build the compared to object centers, and matching is easier since it's involved the 2D information. And some disadvantage like that it requires the large number of views. Then we can have some matching scheme, something like geometry based, which is employed the geometry features, or appearance based, as I shown here, which is represent the object from many possible viewpoints, as I shown here, and illumination direction using the dimensional reduction. You see that if you see from the different point, then the illumination will be one fact that we should not forget about it. And for the geometry base also, you will see that there's some geometrical features will come out. Talking about geometry-based recognition, we can say that in that we have two jobs. One is that we can identify the group of features from some unknown sense, which these can be approximately match the group of the features from model objects, suppose some correspondence. And somehow it can recover the geometric transformation that the model object has undergone and look for additional match. See the models and sense that we have done at below. Then 2D transformation space. In that we have the rigid transformation with 3D parameters. Similarly transformation, which in that we have 4 parameters, and affine transformator, we have 6 parameters inside of them. About the matching, then we should pass some main step. Um, you will see that here I have one image as the entrance, and then from in this image I should extract some features, or we should note down some important character or some important part, or we can say we should take some notable things which will be different from other image as the first step. Then this feature should enter to the model base, model database, and now the matching process will be started. In this matching process, we have some hypothesis formation, something like candidate model, and then hypothesis verification, which all these two bugs, I mean the two last bugs, will be the matching part, main step that we should follow, and we should work with that. Then this recognition um, can be followed by 2 bucks of hypothesis generation, which is identify of one or more model or hypothesis, and hypothesis verification, which tests are performed to check if a given hypothesis is correct or not. Let us see some example about this hypothesis verification. As you will see, features that which we can have might correspond to 2 points. One can be the curvature extra or zero crossing along the boundary of an image that I shown here from the sense and the models part. And another one can be some intercept point, which can be match here. Let us see the image here. Supposing match one, I could take 4 points, which is match the sense, and in match 2, I have 2 points, which is they are match between the hypotheses that I had. But how to choose the sense groups, which is the hypothesis of generation, it's something that we should consider and think about it. These can be followed by some question like this: do we need to consider every possible group, or how to find the group of the features that are likely to belong to the same object? Then in that, we can have some grouping scheme which might be helpful, or some local description that will be helpful. Then now we should decide that you are going to the group or you will go to the local description. Then in grouping, if we go, we should imply non-accidental properties based on the perceptual organization rules to extract the group of the features that are likely to come from the same object. For example, orientation or collinearity and parallelism, proximity and convexity. You will see here, which is it's about some papers in 1996. They say the grouping jobs from the symmetry, similarity, proximity, and closure and smoothness part can come. Or if we go ahead, how to organize and sketch the model base will be the main jobs here for the hypothesis generation. We can say that do we need to search the whole database of the model, or how should we organize the model database to allow for the fast and efficient storage and retrieval part, which indexing in this part will be more helpful and applicable. Yes, go ahead. Then recognition by alignment is approach which is seeks to recover the geometric transformation between the model and the sense, which is using a minimum number of correspondence and assuming affine transformation. Three correspondence are enough for us. This is something that is the result of one more paper, uh, which is put it as the reference of this part. Recognition using the alignment, you can see under the assumption that objects are flat and the camera is not very close to the object. Different 2D views of a 3D object can be related by an affine transformation. We can see them here. And need at least 3 correspond to recover the affine transformation. You will see these 3 dots that I put here recover the affine transformation for us. Then if you want to do the recognition using the post-clustering, which is perform the voting in transformation space, the correct transformation brings into the alignment a large number of features, and incorrect transformation brings into alignment a small number of features. Transformation that can bring into the alignment a large number of features will receive a large number of votes. Then in that, we have some voting system in clustering, which is based on that we can design. If you want to put the steps or name the steps in the post clustering, we can say that in the main step, we have quantized the space of the possible transformations. Usually we use in 4D and 60. Step 2 can be for each hypothetical match, we will solve for the transformation that aligns the match features and cast a vote in the corresponding transformation space bin. We will find the peak in transformation space as the next main step. Suppose we have some models and sense, as you will see here. We show the model with M and sense with the S in this figure. It's something like that. With the model 1, we will start from model 1, M2, M3, 4 to 5. As the larger of the votes also will come to picture. And with the sense also, we have the voting system based on that. One model on one more parts that we talked, that was indexing based recognition, which in that we should, based on the model, compute some index and store it in the form about the models and group, and then which can be stored inside of our model database. These parts which we take the features or indexes from the model, we call it preprocessing, and then we will put it in the model base as the hash table. We will put in the sense that we can put it there, and then recognition will be based on compute this index, and then the unknown object will be created based on this indexing job. Or in the pre-processing steps, the group of models are used to index the database, and then the index location are filled with integers containing reference to the model objects and information that later can be used for recognition. In the recognition steps also, we have the group of sense features which are used to index the database, and the model object listed in the index location are collected into the list of the candidate model. Indexing based recognition, which is ideally we would like the index compute from the group of models features to be invariant. For example, its properties will not change with the object transformation or viewpoint change. Only one entry per groups need to be stored in this indexing part. Geometric hashing is the indexing which is using the affine variable, and indexing remain invariant under some affine information, which in that each triple of non-collinear model points from the basis of coordinate system that is invariant under the affine transformation we'll use, which in that we represent the model points in an affine invariant way by rewriting them in the terms of this coordinate system. As you will see here, we have pi minus p1, and then we have the u and v, which are the affine invariable function based on the other points of p2 and p3. Then this p1, p2, or p4 and p5, which we'll take and put in the hash table and as the index, and then when we retry this index, then we can construct the image once more. In this geometric hashing, we have some steps of the pre-processing step, which for each model, we should do two jobs. One is that we should extract the set of interest point. And the second is that for each order set of three non-collinear points of P1, P2, P3 are considered. Like that, in the first step, we will compute the coordinates of u and v of the remaining features in the coordinates frame defined by the model basis of P1, P2, and P3. Second step will that after proper scaling and quantization, we will use the compute coordinates u and v as an index to a two-dimensional hash table and record in the corresponding hash table B information, some models, and P1, P2, and P3 point. Yes, the next here we shows how this hash function for HU and V will work, which it consists of the scale and quantization of the points, and then we will go with the minimum U and maximum U, minimum Y and maximum Y, and put them in this hash table. Then we have suppose one part of or one block of this table, which is consists of the models as well as P1, P2, and P3. Then we have P3, P2, P4, and then we have P1, P2, P3, like this, and etc. Will be the pre-processing steps for all. Then in the recognition steps, we have extract a set of interest point. Then we will choose an arbitrary order pairs of P prime, P1 prime, P2 prime, and P3 prime. And then we will compute the coordinates of U and V prime for remaining features point in the coordinates frame, which is defined by image basic. After this proper scaling and quantization, we will use the compute coordinates as an index to hash table, and for every entry of the model P1, P2, and P3, we will find some corresponding bin, something like the cast vote there. Then you will see that the tables, the object features will note down inside of hash tables, and then again will be extract to generate and do the recognition process for us. Uh, the 5 steps in geometric hashing is the histogram, which all hash the tables entires that receive one or more votes. Find those entries that received more than the certain number of votes, and each such entry corresponds to the potential match, something like hypothesis generation, as we have here. Geometric hashing or recognition steps has the 6 parts. It can be for each potential matching, for example, hypothesis, and recover the affine transformation, something like A. Suppose we can use some method like SVD that allows the corresponding model sense interest point, and then we can reach the P1 prime, P2 prime, and PT prime. Um, Next step is that we can back project the models onto the sense using the computed transform and compare this model with the sense of find additional matching, which these steps people will call it verification steps. And if verification fails for all hypotheses which we have in step 5, we should go back to the step 2 and repeat the procedure using the difference group of the sense features. Again, the process that we have, and now something like example is like that. We have some model, and then we have some sense, and it can be something as the output that we can have. I mean, that shape is something I don't know, uh, which will be not recognized easily there. But what we have some bad hypotheses with this dashed line, and we have some good hypotheses with this dark color, which in that you can do the uh, recognize some object there. Then we have some complexity, which in that we pre-processing steps we have and recognition steps based on models, model points, and the sense points. We have this formula, which based on that we can find. And something which is happened, they call it unstable basis triples, which in that skinny triangles lead to instability in the computation of the affine transformation uh, parameters. Solution is that we can have some skinny triangular, something like that. We can have to recognize the jobs. And um, again, we have one more thing that we should see, which is the non-uniform distribution of the invariance, which might be, you know, that this distribution of this uh, invariance might be non-uniform, which is increase the number of collisions and number of hypotheses there. Then we have the rehashing, which we will map the distribution of the invariance to the uniform distribution and need to make the assumption about the distribution of the invariance, which I take from this reference. And we should learn the geometric hash function. You can also use this reference. Let us see some original one, which has the affine and similarity. We have the rehashing jobs here, and learning part has the non-uniform distribution of the hashing system. What we should now consider its effect of the noise. As you know, the performance of uh, geometric hashing uh, degrades with the noise in coordinates of the interest points. Then to solve that, we can have some possible solution like that, make some additional entries during the pre-processing, something like increasing the storage, and cast additional votes during the recognition, which is increase the time. Then based on these two possible solutions, we should decide how to move and find that. Uh, we have one more concept, which is the index selectivity, which is that recognition accuracy can be increased by select the good index and proper ones. Suppose for the higher dimensional indicates it can be useful more. And then some method like SIFT will come to pictures, which is the object recognition uh, parts. What is that? In the SIFT, we are match the individual features from an image to the database of the SIFT features from known object, and which in that we will find the nearest neighbors. Then we will find the cluster of the SIFT features belonging to the single object, which is the hypothesis generation. And then we will estimate the object pose, recover the transformation that the model has undergoes, and using at least 3 matches. The step 4, we verify that additional features agrees on the object pose. Then to search for this nearest neighbor, we need some linear search, which is to slow for the large database, or we have the KD trees, which is slow for the K, which is more than 10. Um, What I'm going to tell you this in this lecture, it's little bit will be more theoretical part of this image recognition, and the parts that we need to really detect the object. We have some code, but I just want that you know this type of data or this concept. For the nearest neighbor search, which is the method that we have, the approximate of the nearest search can be best fit of that and examine the n closest bins of the KD trees, and we will use the heap to identify bins in order to their distance of the query. Which in that we can speed up the factor of 1,000 while finding the nearest neighbors of interest of 95% at the time. This is also the result of the paper, which in that they will say how it can affect. Suppose if we want to estimate the object position, we can give the features match, something like this, which is find the cluster of the features corresponding to the single object and solve the transformation uh, uh, part, something like affine the transformation. You will see that first they will take some features, put it in some hash tables, something that we have, and then they reconstructing and took them to make the image. But what we need that we need to consider the cluster of size greater or equal to 3. And how do we find these 3 match our little bit maybe techniques that depends on the techniques that we will use. Um, in that we can have pose clustering, which each feature is associated with 4 parameters: 2D location, scale, and orientation. And for every match, we have MI and SJ, which in that we can estimate the similarity transformation between MI and SJ. And then based on that, you can have Tx, Ty, S, and theta, and then vote them. Means that location of them, scale, and orientation, and give the votes from your system. Something like this, which is the transformation scripts. As we know, it has the 4D. We have the 4 elements. And here are the votes that you can take based on the feature that you select. Then in this estimated object position, we can have the partial voting also, which is vote for the neighboring bins and use the large bin size for the better tolerable errors. And transformation that accumulate at least 3 votes are selected, and hypothesis generation, which is using the model sense match and computes object position. For example, affine transformation and apply the verification part. For this verification, we need some back projected models on the sense and look for the additional match and discards the outliner by imposing the stricter matching constraint. And then we should find match by the refined and the transformation computed parts. With in this part of verification, we should evaluate the probability that match is correct. Some methods like Bayesian and probabilistic models will be used to estimate the probability of the model, and which, as you know, Bayesian models takes into account of the object size in image, texture region, model features count in database, and accuracy of the feed that we can have. Um, what we can have, this is the planar recognition that I'm going to tell that in the next part of uh, today lecture, uh, and we should continue in the next lecture of today. Uh, just before I stop for the first lecture and give you some rest, please turn on your camera that we can do the attendance, and then we have we'll have 10 minutes rest, and then uh, we'll come back for the 2 day lectures, talking for the exam, and we have some work to do, some lot of work to do. Provide the robustness of the models, and a fine model is no longer available here in this 3D object recognition method. Suppose recognition under the occlusion, you can see here that maybe some wrong detection will happen here. And illumination invariance also, you will see the effect of that in this image. And then uh, like that we can do. As we say in object categorization, we have variety of the object that we can do the categorization between them. And one more models that people will use it. This is BOF, or bag of features, which in that it's good for the object categorization. It's something like that. We have one bag, and some features from the main pattern, suppose this figure, can be put inside of my bag, and then I'm searching for these features or these critical points inside my um main figure. Uh, Something like this, suppose texture recognition we can do, which is texture is characterized by a repetition of some basic elements of the text tone, and many times it's identified the text tone, not their special arrangement that matters. Suppose like this, if we want to take the features, these are the features that you can take from this image, or below you will see about each pattern that what feature they will take to recognize. Then here you will see that in this texture recognition, you will see the rate of the each patterns, and then based on this you will decide, based on the quantity of this pattern, you will decide that which texture is selected for you. Some document retrieval is another one, which is the orderless document representation, and frequency of the word from the dictionary can be searched on that. Some words, as you will see, freedom, I don't know, war, and like that. And based on that, you can do this document relative methods. And BOF, we said that it's good for the object categorization, and need some visual dictionary for that. It's another method that can be used for us. Something, if you want to go more deep for this BOF method, which is nice things, you will see that as the main step, we need to categorize the object in the terms of parts or local features. Suppose from this pattern or this image of the pictures that we have, that was suppose around around 6 features that they take. Suppose from bicycle they take this much features, and this from this violin also they take these features. And then in step one, first they will extract the feature. For example, something like SIFT features, it can come out. Some feature will be extracted. In step two, they will learn the visual vocabulary. Suppose These are the main pattern that we have there, and then we will do the feature extraction and clustering jobs. Then we have some visual vocabulary, something like that. Now we have the feature in some book, or we have some clue to search for the inside the image. Then as these features can come and classify for us or put something like that. And then based on this and clustering job, which something like that, we can make the domain between them, or we can make the separate borderline between the figure as the another step. And then each cluster can be searched or compared with the visual vocabulary of the cluster contents, and we will find that in this image which feature is more. And simply based on that, you can find the image. For clustering, let me tell you very brief about this. People mainly they will use the k-means clustering, which is that randomly they initialize the k cluster centers and iterate until the coverage means that assign each data point to the nearest centers and recompute each cluster center at the mean of all points which is assigned to it. And in that, suppose which can be used in the BOF part, in step 3, we will use the quantized feature which using the visual vocabulary and represent each feature by the closest cluster center. You will see here the represent image by the frequency of the visual word. Suppose in this image, how many features of this part is present, or from bicycle parts, or in the bicycle parts, which feature is more, rate of that is more, or in the violin, which part is more. Then simply they can say, and as the main steps, they will find based on the frequency and the code words, they can detect the object based on that. But how do we use the BOF for object categorization? We can have something like that, that each model's category we can have based on the histogram part or frequency of the repeated based on the visual part in each class from class 1 to class n. And then in the models space, we can say that which class puts where in our models. Then the nearest neighbors or NN classifier can be used on this classifier, and winning class will come to some color like pink color, which assign the neighbors to the nearest training data points to the each set of data, and based on this you can select. But for the nearest neighbor, there is one method that they call it KNN, or K nearest neighbor classifier, which in that they will find the K closest points from the training data and label the key points both to classify, and works well provided there is a lot of data and the distance function is good. Let's go next. If you want to see the function of comparing histogram, you can see the formula that I'm not going to describe inside this formula, but you can see some example of detecting here that how they detect the objects and faces based on the recognition part. In practice, the subset of all possible appearance will be used, and the image are highly correlated or maybe compress them into the low dimensional space that can capture the key appearance characteristics and use the some method like PCA parts. What I tell you today, that was very fast and very, what we can say, just I highlighted some point for you. I didn't want to go exactly inside of that, especially some words something like k-means and KNNs, which I wanted that you hear, listen, maybe you can even search for them to take the better concept. Something like visual vocabulary. These are the key factors which mainly use in deep learning subject. And if you had that subject, it will help you to convey that. We have some MATLAB project that I think we can do it in the next what we can say next lectures, that how we can do the color detection. It's actually from one web page that we test, and I found that maybe it will be interesting for you, because some part of that is the box which can do the object recognition and object detection part. It's related to our topic, but we can have some demo regarding that. This example is about the detection of some specific color with other different color on some image, and color detection is uh, necessary in some application, uh, and what we select here, we will select some specific colors on objects. Suppose we have some red colors, as they say here, we can detect in this code. And also with this process, each colors will be detected automatically inside the MATLAB. This is the code that now, let me show you my MATLAB. Can you see my MATLAB interface there?
Yes, sir, we can.
Okay, good. Now let me run the code. I have one shape, as you will see later, that in that I have the colors, and based of the edge color, and features that I will take, I can detect. Okay, let us see first what is my code. I take some subtract from the reading image, and then what we can do, we change it to the gray, RGB to the gray, and then we use the median filter to filter out it from the noise. Then we are going to display the image here, which is this one is my image. Let me run it. Yes, this is the image that I have, lots of color as well as the different shape. Now on the next, we are going to find the bounding box and centroid one, and then we will put some rectangular uh, with the red color, and then edge color with the red, and a line with two, which can be the identifier that we use here. I mean, as you will see, when I detect the red object here, I will put some rectangular, but the rectangular is on such a way that it can cover all my figure. As you will see here, suppose, because the main pattern also was rectangular, let me make it big here. That was big. Then if really I want to do it better, I can change this rectangular R to some other color, something like B. Then maybe it will be, yes, here. It's more visible now. You will see that the red colors one will identify with the help of this rectangular that I put. And then we put the X and Y even dimension of them, a coordination of them, X and Y for each rectangular that we generate. It's good to detect the color which are red in my image. That was one application for the color detection job. If we want to see that in the code, we put the IM subtract and then use the colors. If we want to have the gray color as the RGB color, we can just change the second channel. Suppose that, RGB we have. Then the green color is channel 2 that you can just change this data. And here you will see I detect the green color. Okay. Then the next one is the blue. If I want to select the blue one, simply I can do this as 3 and then do the blue one. Now you will see I can detect the blue color there. This one, which is because it's a little bit combination of the blue and the red one, maybe it's become little bit wrong answer for me, but for the red one, pure red one, it's completely work proper. Then let me go ahead little bit here. And then X and Y coordination has also been shown in the some color change that tell us what should be the dimension of the detected color object inside the image. If, as I have done this, we want to detect the blue one, you can change that color parts to the 3. And this photo for the red color and purple ones are also selected because it has the some majority of the red in that. Some problem that I tell you, because it's mixture with the red and blue, then in the blue one it will take. But red one is okay. That was one example. Another example will be detect the circle in some image. Suppose I have one image like this, one bicycle, that obviously bicycle should have the circle inside of that. And what we are going to find a circle. So we use some image of bicycle. And as we can see, there are 2 circles in this image, with now we can detect them. Now, let us run this code and see what we want from this code. First is detecting the bicycle. Second is that we want that it's give the some info, right, X and Y of this bicycle. Let me do the clear all and close all option there. Go ahead. Okay, yes, I know the problem. Problem is here. I forgot to put the proper one. Then remember, we have 2 points. One is that we should specify the circle. Another one is that we should give the dimension. Yes. This is what we detect. We detect one circle inside of that and also the dimension. You will see center dark and ready dark is have this dimension, and it will give the information of the image for us. You can test on different shape, and then it can detect the circle if it's available there. Here, as you can see, both circles are now detected and are marked with the red and white line, as we have done. And the comment that we use is IM find circle, which it has the RMIN and RMAX, means the minimum maximum radius of the circle, and it will detect only the circle which will lie in the range of the other circle will be ignored. Suppose what here we had one circle here, but this one will be come out. And also intensity you can tune that here, suppose we use the 0.90 intensity for our figure. Next example will be image zooming with bilinear interpolation that I think now we don't have much more time. I will put this example for you on the PPT. If you want, you can review them, I think, yourself and review this example as the self-study part. Anyway, I use some reference for today, like Raphael's and Gonzalez books, and also some other white papers and some research paper. And especially I use the math work